Okay, so this lecture is going to be talking about the model. Start over. This lecture is going to be talking about atoms. So atoms are the fundamental building block of all matter. All matter in the universe is made up of atoms. We are made up of atoms. Desks are made of atoms. Cell phones are made of atoms. Computers are made of atoms. Anything that is a thing in the universe is made of atoms. That includes the air, gases, different things. And so we're going to be talking about a simplified version of an atom. When you get into chemistry, you're going to be talking about much more detailed models of atoms, but we're going to talk about a simplified version of atoms, or a simplified model of atoms, and it's called the Bohr model of the atom. Niels Bohr was a scientist. We'll study about him a little bit more in the next chapter, but he's the one who came up with this model of the atom, and it works pretty well for our purposes. So atoms are made of three smaller particles. They are the electron, the proton, and the neutron. And I'll mark them on our picture here. So this is an electron. And we'll write it here. And I apologize, I'm trying to kind of learn how to use this software. That is an electron. It has a negative charge. Okay. Then we have a proton. It has a positive charge. And we have neutrons, these little blue things. Oops. Okay. The protons and the neutrons are located in the center of the atom, and the center of the atom has a special name, and that is the nucleus. And so that's kind of shown by this purple line here. That's called the nucleus, and that is where the protons and the neutrons live. The nucleus isn't a physical thing, it's just the area where the protons and neutrons are together, and it's at the center of the atom. The electrons live outside of the nucleus, and they orbit around the nucleus in energy levels that we call shells. So hopefully that gives you a little bit of an idea of the starting point of what an atom looks like. Now I'm going to clear this off, and we're going to go to our next page, hopefully. Okay. So the next page tells us a little bit about what we talked about previously. So the nucleus is the central part of the atom. It's very dense. It has protons and neutrons in it, and protons and neutrons are very, very large compared to electrons. Protons and neutrons are about the same size. They're located in the nucleus. Again, we said protons had no charge. We said protons have a positive charge, neutrons have no charge. Okay? And they're about the same mass. We've got the electrons that orbit around the nucleus in shells. So the electrons have a negative charge, and they're constantly moving or orbiting around the nucleus in energy levels that we call shells. Electrons are very tiny compared to protons and neutrons. It takes about 1,800 electrons to equal the mass of one proton or one neutron. So they're very, very tiny. They really don't contribute very much mass to the atom at all. And so when we talk about the mass of an atom, we're only talking about the mass of the total protons and neutrons that the atom contains. Okay? We talked about the shells, and so these are the shells, and they're energy levels where the electrons are living or orbiting around the nucleus. The shell that is closest to the nucleus has the lowest energy. So in our case here, the yellow shell has the lowest amount of energy, and as we move further and further out from the yellow shell out to the pink shell, out to the gray shell, we're gaining energy. So electrons that are in higher energy levels or higher shells have much more energy than electrons that are in lower shells. Okay? We have a special name for one of the shells. So the outermost shell, the shell furthest away from the nucleus that still has electrons in it, is called the valence shell. That's important because the electrons that are in the valence shell are the ones that are going to be involved in chemical bonding, and we'll talk about chemical bonding in another lecture. So the valence electrons are those electrons that occupy the valence shell. So in our example here, this pink shell is the valence shell. And these are the valence electrons. So this particular atom has 4 valence electrons. It has 4 electrons in the valence shell. Those are the valence electrons. Those are the ones that are going to be involved in chemical bonding if this atom is going to bond with anything else. Okay, off we go. Okay, so a little thing about, or a couple of ideas about electrons. Electrons occupy the lowest available shell that they can occupy. So when you're building the model of an atom, you always start putting electrons in the lowest shell that has room available. And there are some rules about how we put electrons into shells. So the first shell, which is our yellow shell here, can only contain 2 electrons. Once those 2 electrons are in that first shell, any remaining electrons have to go into the next shell or the next energy level. And so in this case, this atom has 2 electrons in its first shell, and it has 4 electrons in its second shell. And that second shell is the one that we call the valence shell. The second shell can actually contain up to 8 electrons. So if we had an atom that had more electrons, they could still reside in that second shell until we hit a maximum of 8 electrons. And then any electrons after that would have to go into the next shell out. Okay, so our third shell, which is our gray shell here, for our purposes, it can hold up to 8 electrons. It actually can hold more electrons, but we will not be talking about any atoms that have any more than 8 electrons in its third shell. When you get into chemistry, you'll learn all about the rules for how energy levels are populated, and it gets very complicated as soon as you reach the third shell, and that's why we're not talking about it. All of the atoms that we're going to talk about contain a maximum of 2 electrons in the first shell, 8 electrons in the second shell, and 8 electrons in the third shell. Other than that, you will learn more in chemistry. And it's actually very interesting, but it's much more complicated than we need to learn here. So the other thing you need to know is that atoms are happy when they have a full valence shell. So that means the outermost shell that has electrons in it, if it is full of electrons, so in this case, our valence shell is the second shell, and our valence shell can contain up to 8 electrons. This atom here is not happy because it only contains 4 electrons. 1, 2, 3, 4. It actually wants 4 more electrons. If it had 8 electrons in this pink shell, then it would be happy. Okay? And the reasons atoms bond with each other is because they're trying to fill up their valence shell and become happy. And by happy, what it means is they're achieving a lower energy state. Okay, so let's talk a little bit about the periodic table so we understand how to read it so that we can actually build models of atoms. So on the periodic table, you're going to see a letter or 2 letters with a small number and then a larger number in there. So this letter is actually the atomic symbol. It's either a single capital letter or 2 letters, where the first one is capital and the second one is lowercase. That actually tells you the name of the element that you're talking about. So in this case, this is our atomic symbol, and it stands for carbon. Okay? Then we have an atomic number. The atomic number is the smaller of the 2 numbers that you see on most periodic tables. You have to be careful because some periodic tables contain more information than just what I'm showing you here. So in our case, the atomic number here is 6. And what that 6 indicates, it's the number of protons in this element. So carbon has 6 protons. Carbon will always have 6 protons. If you have an element, it has 6 protons, it is carbon. It's not anything else. If it doesn't have 6 protons, it's not carbon. Okay, so the atomic number, or the number of protons, tells you exactly what element you are dealing with. Okay, then we have the atomic mass, and the atomic mass is here. And that number looks a little bit scary, but it's really not. It's actually a weighted average of all of the atomic masses of the isotopes of that element. Essentially, what we're going to use it for, it's going to tell us the number of protons and neutrons that are contained in the element that we're talking about. So let's clean this off. We'll go to the next slide. Okay. So what we can find out from the periodic table, we can figure out the name of the element that we're dealing with. It tells us how many protons that particular atom has. And then if we look at the mass number, which is the number down here, that actually tells us the number of protons and neutrons contained in that atom. So if we know that we have 6 protons, and that we know that we have a combination of 12 protons plus neutrons, we can figure out the number of neutrons by taking the mass number and subtracting the atomic number. So in this case, if we wanted to find the number of neutrons, we would take the mass number, which is 12, subtract off the number of protons, and that means that carbon has 6 neutrons. Oops, there we go. So that's how we figure out the number of neutrons in our atom. Okay? Hopefully you're still with me so far. So one last thing that I want to tell you about in this is that if I'm dealing with a neutral atom, so a neutral atom means that the number of protons is going to equal the number of electrons. This is very important. So remember we said that protons have a plus charge, and we said that electrons have a minus charge. So if we have the same number of protons as electrons, what we're saying is we have the same number of positive charges as negative charges. So overall, our atom is neutral. It doesn't have a charge imbalance. Okay? And when we're drawing Bohr models of atoms, we're drawing a neutral atom. And so the number of protons is going to equal the number of electrons in our model. Okay, so let's go ahead and practice drawing some of these models. Okay. So let's draw a Bohr model of helium, and we'll see what it looks like, and then we're going to figure out if it is a happy atom. And remember, happy means that it has the same number, happy means that the valence shell is full. And so if I look on the periodic table, I can see that helium has an atomic number of 2, and it has an atomic mass of 4. And so what I do is I'm going to start out by drawing the nucleus. So here's my nucleus, and inside my nucleus I have the protons, so I have 2 protons, and I also have 2 neutrons, okay, because my atomic mass minus my atomic number gives me the number of neutrons. So this is inside my nucleus. Now I'm going to go ahead and I'm going to draw my electrons. I'll draw them in a different color. I'll draw them in red here, okay? And so my electrons are going to be orbiting around the nucleus. And so here is my first shell, which is the lowest energy shell, and that's where my electrons are going to start being populated. So I know that if I have 2 protons in my helium atom, and my helium atom is neutral, I also have to have 2 electrons. So I'm going to go ahead and draw my 2 electrons. So here's one electron, and here's my other electron, and I'm done. I had 2 electrons, and they were both able to fit in that first shell. That first shell is now full. That's my valence shell. It is full, and so helium is happy because it has a full valence shell. Okay, does that make sense? Hopefully it does. Let's move on. Let's try beryllium. And I'm going to need Okay, so we're going to go ahead and we're going to try to draw a Bohr model of beryllium. So looking on the periodic table, here's what beryllium looks like. The atomic symbol is Be. That stands for beryllium. The atomic number is 4, and the atomic mass is 9. So what does that tell me about the number of protons in beryllium? It tells me that beryllium has 4 protons, and that beryllium has 5 neutrons. And the way that I figure out the neutrons is I take 9 minus 4 equals 5 neutrons. Okay, so let's go ahead and we'll start drawing this model. So we know that the protons and the neutrons go into the nucleus. So we're going to go ahead and we're going to draw a nucleus, and we'll draw it in blue. And we know that we have 4 protons, and we know that we have 5 neutrons. And so those all sit inside the nucleus. And now we've got to figure out how many electrons this beryllium atom has. So we know that it's a neutral beryllium atom, which means that the number of protons is going to equal the number of electrons. So we have 4 protons in beryllium, therefore we're going to have 4 electrons. So we need to start putting these electrons into their shells around the nucleus. And so remember we said that the first shell can only hold 2 electrons. So we're going to go ahead and we're going to draw those 2 electrons. 1, 2, oops, I just moved it off. But I still have 2 more electrons that I need to draw. The problem is this shell is full. I can't draw any more electrons in this shell. So I need to have another shell for beryllium. And my remaining 2 electrons are going to go in this second shell. So here's 1, and here's 2. So now I'm done. I've drawn all 4 of my electrons for beryllium. 2 of them happen to be in the first shell, and 2 of them happen to be in the second shell. And so the valence shell is this second shell, this outermost shell, and we'll label it here. So this is our valence shell. And so beryllium has 2 valence electrons. But we remember from before that this shell can actually hold a total of 8 electrons. And so this atom is not happy yet. It would want to have a full valence shell, and it doesn't because it has 2 electrons in its valence shell. It can have up to 8 in there. So beryllium, as it stands, is not a happy atom. So I'll let you guys try chlorine and see what you can come up with. Okay? If you have any questions, let me know.